on this computer. Okay, seems to the recording might be bogging down my side a little bit, so that's why sometimes I don't hear everything clearly. So, but please make good use of the chat room. I'm pretty good about answering those questions. All right, so it's week 9. Okay, early voting has started, by the way. Early voting is in San Marcos. Let me share my screen real quick here. There's at the PAC. There is also, let's see, early voting this week, share. So if you're on campus, the PAC on campus has voting days today, the 24th, 25th, and 26th. So if you want to early vote on campus, there's that. There's also the health center. If you're out by the hospital, there's we also have it today, 24th, 25th, and 26th. And then at the Hays County Government Center, which is also on Wonder World, it's today, 24th, 25th, and 26th. So if you haven't already done that, go ahead and try to schedule some time to make sure that happens, okay? I'm gonna stop sharing and admit. There we go. So today we're gonna continue with chapter 6, and we're gonna finish up chapter 6, and we're gonna start a little bit on chapter 7 today. And then you should start to read module 7. I've uploaded slides for module 7.1 and 7.2. I should have 7.3 and 4 up by the end of the day. The homework is not due for module 7 until October 26th. The homework due for 6.2 is due tonight at midnight. There was a glitch somehow. It was only letting you attempt once up to this point for 6.2. 6.1 had already closed, but if you want to go back and check your answers on 6.2, that has been changed to 2 attempts before it actually locks you out. So if you were concerned about that, go ahead and go back over some of that stuff. It's only 39 questions, so so that you can check the ones you weren't sure about before then. Okay. Any questions about what's due this week? Okay. So for this week, we're going to have a couple lectures on alkenes and elimination reactions. We're going to introduce those topics. And then on Friday, we have an activity called SN1, SN2, E1, E2. And we're going to do that on Friday for the second half of Friday. It's basically because the mechanisms seem to overlap a little bit between substitution 1 and 2 reactions and elimination 1 and 2 reactions that we'll see. I have an exercise to help clarify things in your head, what to look for. For example, strong bases if you're looking for elimination, or good nucleophiles looking for substitution. And so we're going to do that as an activity on Friday to try to hammer all these ideas down in our head. Okay. So that is what we're going to be doing this week. And then we're going to finish up module 7 next Monday. We'll have a review on Wednesday on our third exam. I'm sorry, our second exam is on October 30th. Okay, Friday, October 30th during class time. So that's coming up in a couple weeks. All right, any questions about that before we head on into our reactions here? Okay, so I believe we had just finished up SN1, SN2 reactions, and we had talked about at the end of that we had some, you could do an SN1, SN2 reactions to make a ring, and that you had these groups that were, if the substitution center was adjacent to an sp2 hybridized carbon with either an arene or a double bond, it actually enhances the rate because it stabilizes that in that transition state or that intermediate. Okay. So that being said, we're going to talk a little bit more about converting sp3 hybridized carbons into sp2 hybridized carbons. And that's all about elimination reactions. Okay. So let's see, this is number 1 right here. So I'm going to go ahead and share my screen with my iPad. There we go. So again, 7.1 and 7.2 modules are posted on, let's see, my slide disappeared. Where did it go? Uh-oh. I'm going to stop sharing and reshare. It seems to have locked up for me here. There we go. I see it now. All right. So like the name implies, elimination reactions are not like substitution reactions. What we're going to end up doing is we're going to lose two atoms. And in the process of losing two atoms, we're going to create a double bond. Okay. So this is kind of 7.1 isn't on. Oh, it's not on Canvas yet. It's posted to Top Hat right now. I will get it onto Canvas by the end of the day. Thank you for reminding me about that. Canvas. Yeah. It's just, yeah, I haven't posted it to Canvas. Sorry, I forgot about Canvas. All right. So let's talk about the general concept here. And so basically, just like in a substitution reaction, we have a leaving group. Okay. Most of the time we have a leaving group in these systems that we have there. And so we're looking for some of the same things we're looking for in a leaving group of a substitution reaction, like loss of a stable ion or something like that. But the other leaving group we have here is we usually lose a hydrogen. Okay, so a hydrogen that we lose is on the carbon 1 over from the leaving group. And in the process we're doing this, we're going to leave the electrons between the hydrogen and that carbon behind. And those are the electrons that are used to make the double bond. Okay, so the entire process is typically we're losing sometimes acid or water. And so we have special names for those. But the entire process itself is called elimination. Okay, so we are eliminating two sp3 hybridized carbons and turning them into two sp2 hybridized carbons. Okay, and then that means that that pi bond is formed by those unhybridized p's. Okay, so we need to pay attention to where the hydrogens are coming from when we have these. We have to have our hydrogens adjacent to a leaving group, and therefore we have to have a nomenclature associated with that. And so the nomenclature we're using for this is what we call the alpha, beta, gamma system, where the alpha carbon is always the carbon with the leaving group, typically, and when we have, when we're talking about elimination reactions. But in general, alpha carbons are those next to a functional group. Okay, so for example, when we go into next semester and we're talking about aldol condensations and stuff like that, we'll use this alpha beta system quite extensively. So in the case of just a functional group like like this carbonyl here, our alpha carbon is the one over from that functional group. And that makes the hydrogens attached to that carbon are alpha hydrogens. Okay, so notice that we're having this on the alpha carbon is the one attached to the functional group. Then if we go one carbon over from that, we have the beta carbon, and then we have the beta hydrogens because they're attached to the beta carbon. And if we go over one more, we go to gamma. Okay, so we can extend this out to the entire chain if we want to. But in the case of this, we only typically need to go with the alpha carbon and the beta carbon and what's attached to them. Okay, so in the case of this compound here, our alpha carbon is the one with our functional group attached to it. In this case, it's the bromine. And this is what we're going to see in these elimination reactions. We have a leaving group like bromine is going to be attached to the alpha carbon. Okay, now the thing comes up is, where do we remove the hydrogen? The hydrogen has to be removed from a beta carbon. So in this case here, we have a carbon that's 1 over. That makes it a beta carbon, which means it has 3 beta hydrogens on it. This is a beta carbon. This has 2 beta hydrogens on it. This is a beta carbon, and this has 2 beta hydrogens on it. Okay, so that means we have a choice here. We have a possibility of 7 different hydrogens that can come off, giving us 3 different reactions in the end. Okay, so we have to pay attention to where that hydrogen is that comes off in the reaction, that beta elimination site. Okay, so now that we have an idea of where things are going to be, let's talk about how stable or unstable alkenes are. In general, alkenes are not as stable as alkanes. Okay, we have a different hybridization, we have a p orbital, and therefore it's more reactive. Okay. However, within alkenes, we have different forms of stability. Okay, so in this case, we're looking at the idea of comparing and contrasting alkenes for stability by just figuring out what their heat of oxidation would be. So if we oxidize the products all the way down to CO2 and water, what amount of heat would be given off? Okay. So in the case of a terminal alkene, an alkene with just 3 hydrogens and a carbon on it here, we typically see it to be the least stable of the set. And we know this because it gives off the most amount of heat during this process. Now, if we have an alkene with 2 carbons on it and 2 hydrogens on it, that's a little more stable. So going from 1 carbon on an alkene to 2 carbons on an alkene makes it more stable. Okay, and in this case, the trans configuration is more stable than the cis configuration, and that comes to do with, think about sterics there. You have those hydrogens coming off here, starting to butt up against each other. Here we don't have that, and therefore the trans is more stable than the cis configuration. So monosubstituted, disubstituted cis, disubstituted trans. Okay. Now, what's even a little more stable than that would be to get rid of some of the steric and put both of the R group, both of the carbons on the same side of the alkene. This is a little bit more stable, and it has 2 hydrogens on there. And so what we typically call this is an exo alkene, where it's outside of the longest chain, but it's still part of the name. Now, the thing that's more stable than a disubstituted is, of course, the trisubstituted. And then a tetrasubstituted is the most stable alkene possible. Okay, so when we're thinking about thermodynamic products of our system, we want to see it to become the most substituted alkene, if at all possible, in the thermodynamic products. But sometimes we run reactions where we end up with the kinetic product first. So whenever possible, we want to go to our thermodynamic product or the more substituted alkene. But there's a couple places we can't do that, and we'll talk about that in a minute. All right, questions on alkenes and stability. Okay, well, while you're hacking your questions in there, I'm going to go ahead and look into a little bit why these things are more stable. Come on. It's trying to squeeze that thing down. Now, the reason these are more stable, so that table is just to show you that we've measured them to be more stable. So the reason they're more stable is because the adjacent carbons to the double bond can hyperconjugate, or basically share some of their electron density with the alkene. Okay, so if an alkene is less stable than an alkane, just because it has that double bond in here, by helping stabilize that double bond, that alkene becomes more and more stable. So in the case of monosubstituted, you only have 1 carbon available to back donate some electron density. Okay. So in the case of the cis and trans right here, we have 2 carbons available to donate a little bit of electron density back to that pi cloud, but we now have a steric interaction. These 2 groups are sterically butting up against each other, so it's slightly less stable than the trans. And these are far apart, and they are slightly more stable than the trans. But again, they each have 2 carbons that are donating electron density to help stabilize that double bond compared to the monosubstituted. So that's why inherently the trisubstituted is going to be more stable. Even though we have sterics starting to get involved, we have 3 things that can hyperconjugate, donate back to the double bond. And in the case of tetra, again, sterics are a factor, but the fact that you have 4 different atoms donating electron density to that, it makes it even more stable. So we only worry about the steric interaction when we have the disubstituted system. By the time we get to the tri and the tetra, it's completely an electronic factor in the case of hyperconjugation. The sp3 hybridized hydrogens are donating some of their electron density back to that p orbital of the pi bond. Okay, so that being said, we have to have a mechanism that tells us what's going to drive our forces for these eliminations. Okay, so the first mechanism we're going to talk about is we're going to call an E1 reaction. Okay, now This is kind of analogous to our SN1, SN2 reactions. Our SN2 reactions were bimolecular and were one-step concerted reactions. Okay. Our SN2 reactions were one-step and concerted reactions. Our SN1s formed an intermediate, and they formed an intermediate in the form of a carbocation, and it had 2 steps in the reaction and always formed an intermediate. Okay. So analogous to that, E1 reactions also form an intermediate. They are a unimolecular reaction where they form the carbocation first, and after they form the carbocation, then something comes in and pulls a hydrogen away from a beta carbon to make it form the alkene. So let's see if I can blow up this system right here without making it go anywhere. All right. So in the case of this tert-butyl with the bromine on it, let me see if I can blow it up a little higher without having it go anywhere. All right. So the carbon with our bromine on it is our alpha carbon. It has the functional group. Okay. So that's where we're going to have that leaving group leave first. Okay. Now we have 1, 2, 3 beta carbons. And in this case, they're all equal. So it doesn't matter which one we take it on. All we know is that one of these hydrogens on a beta carbon is going to be removed in the second step of our reaction. Okay. But because this is a elimination reaction unimolecular, we're going to have to break the bond between the functional group and the alpha carbon first. Okay. So in this case here, we're using a polar protic solvent. And in this case, we have the ionization of this bond. The electrons that were forming the sig bond are leaving with the bromine to give us the bromide ion, which is a nice stable ion, which makes it a good leaving group. And then it forms this carbocation. Okay. Now, there's a couple things that can happen with this carbocation. Okay. We can react it as a substitution reaction by having a nucleophile. A nucleophile come in and react with it and form a new sigma bond. Or we can have something in the solution act as a base and eliminate a beta hydrogen. Okay. So inherently, we seem to have competing reactions here. But we're going to give you some real nice stepwise things to look through to figure out whether they're going to go into one or the other. Okay. Statistically, it can do either because you formed your nice reactive carbocation. So let's use our methanol as a base first. And what we're going to do is we're going to have that lone pair reach out and grab that hydrogen, leaving the electrons in that sigma bond between that beta carbon and that beta hydrogen there. And those are the electrons that are going to come in and form our new double bond. Okay. So that is our elimination reaction where the solvent is acting as the base. Okay. Now let's look at our solvent. Our solvent's methanol. It has a lone pair. Okay. That means that lone pair can act as a nucleophile also. If it did that, it would act as an SN1 nucleophile, come in and form a new sigma bond with that lone pair, and we would generate this protonated species here. And then we need a little more methanol to act as another base to give us our neutral species at the end. Okay. So that being said, once we use our methanol to deprotonate here, we have our protonated alcohol here. And notice we have our protonated alcohol in the elimination reaction. So SN1 and E1 reactions are in competition with another. However, you can influence it to be one versus the other. Okay. Now, because this is a unimolecular reaction, if we looked at our rate law, it only depends on the concentration of our substrate. It only depends on our concentration of the thing with the leaving group on it. Okay. And so we call it a first order reaction. Okay. So now notice the first step in this E1 reaction is exactly the same as the step in the SN1 reaction, that formation of carbocation, which means all those things that we have that stabilize carbocations, like solvents, protic solvents, etc., are the same solvents that'll help form these E1, E2 products. Excuse me. Okay, so if that's what that looks like, let's go ahead and look at the mechanism in a slightly blown up way here. So again, it's an E1 reaction, unimolecular. Unimolecular means forming a carbocation, okay? Once you form the carbocation, two things can happen. If you have a good nucleophile, okay, like a bromine ion or a high concentration of bromine ion or a high concentration iodine, it's going to do the substitution product, okay? However, when we have these neutral nucleophiles like methanol and water, those are poor nucleophiles, and therefore they can act in the system, not necessarily as a nucleophile, but they can act as a base. In the case of the elimination reaction, the lone pair on our alcohol here is going to reach out and grab this hydrogen, leaving the electrons in to form our double bond. Okay. So that is the two steps involved in that, which means if we looked at the rate law, the coordinate diagram, we would see two humps. The first activation energy of breaking that carbon-bromine bond, giving us our two ions. Then the second activation energy of getting it to have the solvent come in as a base and deprotonating it to give us our final products. Okay, so let's look at these two different possibilities happening in our coordinate system here. Okay, as I said before, the first thing that has to happen is we have to break that alpha carbon bromine bond to give us our carbocation. Okay, so that's that first activation energy here. And that step has to happen whether it's E1 or SN1. Okay, so right now, the reaction looks exactly the same. Okay, so now the second thing that has to happen is we have two things that can happen. We can have our base come in at our beta carbon and that hydrogen on the beta carbon and start pulling away that proton, or that alcohol is going to come in and start forming a new sigma bond. Okay. So if we look at the SN1 reaction here, and if it had a transition state here that was pretty low, it would actually form the SN1 product overall. And if the activation energy of the deprotonation was too high, we would have, it's in a different state here, we would give our overall reaction as the SN1. So the difference here is that we have this thing, our solvent coming in and is interacting with the beta hydrogen first. If it interacts with the beta hydrogen first, we have our E1 elimination. If our base comes in and starts interacting with the carbocation first, we're going to have that substitution reaction. Okay. So in this particular reaction where we have ethanol as our solvent, and again, our same substrate of the bromo T-butyl bromide right here, we actually end up getting about 81% of it being the substitution product because that activation energy is low. Okay. So there has to be a way to kind of tweak the reactants to encourage one mechanism over the other. Okay. So this ethanol is acting as kind of a weak base and kind of a stronger nucleophile, and therefore we only get 19% of our product as the elimination product. Okay. So what does this mean? It means the nature of our base is going to be influencing whether it acts as a substitution, a nucleophile, or as an elimination of base. Okay. If it acts as a base and pulls a proton off, we get elimination reactions. If it acts as a nucleophile, we get substitution reactions. So we have to think about our system as how can we make it less nucleophilic and more basic. If we make it less nucleophilic and more basic, we should get to elimination products as our major product. Okay, So one thing we can think about there is, well, we can actually influence that by changing that activation energy by changing the temperature. Okay, so a higher temperature will of course make a greater number of molecules have that higher energy. And remember that E1 energy barrier was higher than the SN1 energy barrier. So if you take that same reaction and heat it up, you're going to have more molecules acting as bases than acting as nucleophiles, and you will actually increase the ratio of your product uh, as the temperature increases. So let's think about that. Okay, so at lower temperatures, our SN1 is favored because our nucleophiles are not acting as bases. Okay. In addition to that, we would like to do our SN1 is favored when we have tertiary carbons with a good leaving group and a polar protic solvent. Okay. So, and we need a weak base as our nucleophile. Okay. So we're going to talk about weak and strong bases in a minute. Now, so that means at low temperature, we can actually force it to go SN1. Okay. Remember, the SN1 barrier was lower than the SN2 barrier, and therefore by adding heat, we can influence more molecules to go through that higher activation energy. So at a higher temperature, we can get it to act more in that. But also, if we made it a less of a nucleophile, but a stronger base, we can influence it to make it the E1 product. Notice these are both in polar protic solvents because polar protic solvents support our carbocations. Okay. So a lot of times the E1 reaction, the SN1 reaction isn't used, and the E1 reaction is decreased. If you do it, if you control the temperature correctly, you will get a higher portion of your E1 product from the system. If an elimination product is desired, it might actually be better to change your base and try to get to an E2 mechanism. And we'll talk about that as well. So E1s are always in competition with SN1s. However, by increasing the base strength and increasing the temperature, you can get more of the E1 product, but you will never eliminate a little bit of the SN1 product. Okay. So now we know that our leaving group leaves off our alpha carbon, and we know that we have to dig one of the hydrogens off of a beta carbon, okay? But how do we know which one to take? If we have the possibility of making different molecules, we might have a competition between those different things. In our first example there, we had 3 methyl groups and they were all equivalent. It didn't matter where you removed that beta hydrogen, they would give all the same product, okay? But if they're not the same, we have to use a way to figure out what is the primary isomer to get in. There's always going to be a slight mixture, but you're going to get a primary isomer based on the location and number of beta hydrogen. Okay. So let's look at that in a little bit here. So if we look at this concept right here, we're going to keep our 2 methyl groups here, but we're going to add an ethyl group. So now we've changed the nature. We have 2 equivalent alpha hydrogen types right here, but this is a non-equivalent alpha hydrogen type, right? Because it only has 2 hydrogens and a methyl group here. Okay, so statistically, there are 6 beta hydrogens here and only 2 beta hydrogens here. Okay, so statistically, it says you should have a better chance at removing one of those 6 hydrogens than one of those 2 hydrogens. Okay. So let's just look at it that way and let's talk our way through this here. Okay. So of course, in our first step of our E1 reaction, we form our carbocation. So let's look at the carbocation we form. And assuming we don't do assuming we haven't optimized our reaction so it's not enough of the temperature, the first thing that can happen is we get our SN1 product, okay? And that's this gold band right here. We actually had our methanol come in and act as a nucleophile and create a new sigma bond. And then that goes to our SN1 product. Okay, now, so that's one possible reaction. The next possible reaction is we take the hydrogen from the greatest number of beta hydrogens we have, and we had 6 of these from region A and 2 of these from region B. So there's 6 possible alpha hydrogens here. And when we do that, that creates a elimination product where we end up with the ethyl group being over here, a methyl group here, and that last methyl group makes the double bond, and therefore we get this alkene here, okay? It's a disubstituted alkene, and it is, it's our first E1 elimination product. Okay, so statistically, there's 6 of these, and there's only 2 of these hydrogens in our region B here. So there's only 2 there. So it should happen less of the time, right? However, that's not necessarily the case. Because when we remove this hydrogen here and give us our E1 product with the beta hydrogen on the more substituted carbon, we actually get our elimination product as a tri-substituted alkene. Okay. Remember, tri-substituted alkenes are more stable than disubstituted alkenes. So even though statistically there are more beta hydrogens over here, this makes the more stable product, okay? And if this makes the more stable product, thermodynamically stable product, and we're forming that carbocation, so we have time to wait, it's going to give us the more substituted alkene, okay? So this is called Zaitsev's rule. Whenever you do an elimination, an E1 elimination, you will always get the more substituted alkene as the major product, okay? So the more substituted alkene as the major product. The less substituted alkene will be the minor elimination product. But notice in this case here, our major total product overall is actually our substitution product. And that has everything to do with the size of our base here. It's acting more as a nucleophile than a base, and therefore we get more substitution product. And look at the, SN1. Look at the size of this. This is a small. So we're going to start looking at the size of bases as an effect on whether or not it's going to do substitution and an elimination reaction. But when we do elimination reactions, we want to get the more substituted alkene as our major elimination product. So the whole reason we have this happening here is that we, again, have these differences in transition states, okay? So if we look at our first step in our transition state is, of course, the same, our formation of our carbocation. And then if we look at our activation energy of removing the hydrogen on this region A beta hydrogen, okay? So it's basically, we're removing a hydrogen off a carbon that only, in this case, I'm sorry, this is the region B beta hydrogen. We have it pulling the electrons off a carbon that has another carbon on it, okay? So because that carbon has another carbon on it, it actually makes it easier to remove that hydrogen because it's just not, those electrons aren't just coming back onto a bare carbon with just hydrogens. We have that other carbon to help stabilize that breaking of that bond, okay? So in the case of, this is our A region where we're just pulling it off here, it's actually a higher energy barrier to remove this hydrogen because you only have these 2 hydrogens trying to stabilize that carbon, okay? So because you already have a carbon here, it's going to make that hydrogen slightly more acidic and therefore easier to remove. And if it's easier to remove, it has a lower activation energy and therefore generates our more substituted product. Okay. So, and I assume that the substitution product here is even a smaller activation energy. Okay. So the idea here is that our activation energy is lower when we're removing the hydrogen with the more substituted carbon. If we remove the hydrogen from the more substituted carbon, we get the more substituted alkene as our product. Okay, so that's just the kind of theory on how you do it. And up to now, we've looked at our halogen as our leaving group. Okay, and when we have a halogen as a leaving group in an elimination reaction, we call that a dehydrohalogenation. Basically, we're removing a hydrogen and a bromine, so we're removing acid. We're removing HBr, we're removing HCl, we're removing HI. Okay, and so that's the first type of elimination reaction, a dehydrohalogenation. So we're just removing acid to create a double bond. Okay, the next kind of thing we can actually do is we can take away water. Okay, so we take off an OH off one carbon and a hydrogen off a beta carbon to give us a total of H2O and our alkene. Okay, so in the dehydration of alcohols, especially if they're tertiary alcohols, we're looking at the E1 elimination reaction becomes the dominant reaction. Okay, in the case of acid catalyzed dehydrations. Why? Okay. OH is a bad leaving group. Why would it leave? Oh wait, in the presence of a strong acid, that alcohol will be protonated to give us the hydronium or the oxonium cation, and then that leaves as neutral water, giving us our carbocation. Okay, so in the case of having this as our substrate here, it's 2-methyl butanol. Okay, we have 6 beta hydrogens here. We have 2 beta hydrogens in this different zone here. We're going to take this acid, protonate here, and then this leaves giving us a choice of these 2 beta hydrogens or these 6 beta hydrogens over here. And because of Zaitsev's rule, we know that we're going to get the more substituted alkene when possible. And in fact, our alkene is 90% of our product, and our disubstituted alkene is only 10%. Okay. So this actually, the dehydration of alcohols, is a lot cleaner than the dehydrohalogenation reactions when we go through the E1 mechanism. Okay. Now, what happens if we take that tertiary alcohol, which makes it really easy to form that tertiary carbocation, and then we have those alpha betas, and we do it on a secondary alcohol? When we do it on a secondary alcohol, it changes things a little bit. And the reason is that you can have hydrogens taken off here. So let's call that hydrogen 1. Or we can take this off here, hydrogen 2. Okay. When we take it off hydrogen 2, we actually have 2 possible isomers formed. Okay. But we still, our major products are following Zaitsev's rule. Okay. So our minor product is going to be the one taken off this section here, and it gives us our least substituted, our monosubstituted alkene. So, but why, when we have our hydrogen here, our beta hydrogen over here, do we get a mixture of cis and trans? Oh wait, it's going through a carbocation. Carbocations are sp2 hybridized trigonal planar, which means if you remove a hydrogen from the top or a hydrogen from the bottom, you can get either one. Okay. However, notice that the cis isomer is less stable than the trans isomer. So while our disubstituteds are 80% of our product, our major product is still going to be the more stable alkene. Least stable alkene, more stable alkene, most stable alkene in our system. And it's our major product. Okay, so let's look at that mechanism in a little more detail. Okay. Like I said before, OH is a bad leaving group. We're not going to lose hydroxide on the system. So the first thing we have to do is we have to protonate that alcohol, making it a better leaving group. Okay, so when we protonate that alcohol, we actually turn out making the sulfuric acid. We're giving off a proton, right? So this is its conjugate base. That's the base in our system that's going to be pulling off that hydrogen off that beta carbon. Okay, so we've created our conjugate base and we have our protonated alcohol. Now our protonated alcohol can lose water, generating our carbocation. And so that's what we're going to do here. We're going to lose water and generate our carbocation. Okay. So the next thing that has to happen is we have to have a base come in and remove one or the other of the beta hydrogens. Okay. So if our base comes in, and water can act as a base too, don't forget that. Water can come in here and act as a base, and the sulfate can act as a base as well. If it removes this proton from this side, we're going to get that di-substituted alkene like this, because this is a methyl group and this is a methyl group. However, if we have water come in and act as a base on this hydrogen here, the more substituted carbon, we're going to get our tri-substituted alkene. Okay, so follow the color of the electrons here. If we remove the hydrogen on this yellow side right here, we're going to end up with our tri-substituted alkene. If we remove it from our purple side here, I don't have purple, so I'm going to do red, we'll end up with our less substituted alkene. Okay. All right, so do we see why that we get the more substituted double bond? Because it is thermodynamically more stable. Okay, so it's always going to be in the major product. Okay. Do we see that the reason we get that double bond is we are removing a hydrogen from a beta carbon? And do we see that this reaction works best because we are protonating a bad leaving group, turning it into a good leaving group? Water can leave as a neutral species and act as a base, giving us our carbocation intermediate, which then lends us to the products we have. All right. Any questions on that? Okay. So let's look at the reaction mechanism here. I'm sorry, the coordinate diagram, and look at kind of why we think certain things are going to happen certain ways. Okay. Notice in this case here, we are using the sulfate as the base. We are not using the water as the base, so you can use either one. But again, the first thing that happens is we have our neutral species and we add a proton to it here. There took a little bit of activation energy to transfer that proton. And notice this intermediate here is higher in energy than our neutral species because it's a charged species. That's where that energy is, okay? That's the just protonating part. And then there's another activation energy here to lose that water and keep the positive charge on our carbon. Okay. So once we have that, we have a couple different things that can happen. Okay. We can have carbocation rearrangement. Remember when we had SN1 reactions, we talked about carbocation rearrangement. If you have a secondary carbocation and it can move a methyl group or a hydrogen to form a tertiary carbocation, it will. If you have a secondary carbocation, it's not going to rearrange to form a different secondary carbocation. So it's only an improvement in stability. We're going to see that. Okay. So in this case here, all right, what we can see here is in this case, we have a slightly different substrate because we have this T-butyl group here. We have an opportunity to move a methyl group over and give us our rearranged carbocation. Okay. But if we didn't rearrange this carbocation, what would the next thing happen? We would try to remove a hydrogen from a beta carbon. And notice there's no hydrogens on this beta carbon here. There's only hydrogens on this beta carbon. So that would yield us our least substituted alkene. And we only have the one choice for a beta hydrogen. However, notice that the activation energy of deprotonating that system is higher than the carbocation rearrangement. Therefore, if it's going to rearrange to form this tertiary carbocation, now we have a choice of the hydrogen here, which would be a beta hydrogen after the carbocation's moved here, or a beta hydrogen here or here. So we actually have two possible products in our carbocation rearrangement, and those would be the less substituted alkene, because we're removing it from this methyl group on the end, which give you this one here. And if you removed it from the more substituted right here, it would give you the more substituted alkene here. Now, let's look at this product ratio. Okay. Because the carbocation rearrangement was less of an activation energy than just the direct deprotonation, those products are the greatest products. We have, let's see, 97% of them being that. Okay. Only a little bit is this less substituted product that is the unrearranged carbocation. Once we rearrange the carbocation, now we have a choice between two different alpha hydrogens. And whenever we have a choice of two different alpha hydrogens, two different beta hydrogens, whenever we have a choice between two different beta hydrogens, we will always have the more substituted alkene make the higher, that would be the highest yield in the product, okay? So we have our tetrasubstituted is more than our disubstituted, which is more than our monosubstituted. Okay, and for at least two different reasons. We have a carbocation, no carbocation arrangement, and here we have a competition between two different beta hydrogens, giving us the more substituted alkene. All right, so I think I want to stop there because we're going to do stereochemistry next. All right. So questions on the mechanisms. Okay, notice the mechanism is the same. We're forming that carbocation. Okay, so whatever you can do to form that carbocation first, now you need to look at the hydrogens that are on those adjacent carbons, those beta carbons. Where can you remove a hydrogen from those beta carbons to make the most stable alkene? And that is going to be your major product. All right, questions, comments? Can you hear me?
No questions, thank you.
Okay. Oh, I heard that. All right, well, I'm going to go ahead and stop recording. And if you got another class, go ahead and go off, and I will post this as soon as I can.